Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Cohort University of Science and Technology. I welcome you to the course PHY 352, Nuclear Physics 1. Today, it is the 20th lecture of this course, and the topic is spin, parity, and electromagnetic moments of Deuteron. That is, in this lecture, we will be discussing various quantum aspects of the nuclei Deuteron. First, I will give the learning objective. At the end of this lecture, the student will understand how to determine the spin, parity, magnetic moment, and quadrupole moment of the Deuteron. In this course, we are following the book Introductory Nuclear Physics by Kenneth S. Crane, 3rd edition. In this lecture, I have taken some of the illustrations from this book. The measured spin of the nuclei Deuteron is equal to 1. If you remember, that is the total intrinsic angular momentum plus the orbital angular momentum associated with the nuclei that is composed of two nucleons. One is proton and the other one is neutron. Now, the first question is how one measured this spin of the Deuteron nuclei. As I told you in the previous lectures as well, the experimental aspects regarding these various aspects of the various nuclei are discussed in chapter number 16 of the Crane book. But in this lecture, we will be just see the theoretical aspects, or we can say how one can verify these numbers which are obtained through various experiments. Now, by studying the reaction involving deuteron and the property of the photon emitted during the formation of the deuteron, we know that its parity is even. So, if you remember, in last few lectures we have discussed these aspects of the nuclei, the spin, the parity, the electromagnetic dipole, and the electric quadrupole moments regarding the various nuclei. So we have discussed these aspects generally, so you need to refer those lectures where we have discussed, and here we will be discussing these aspects regarding the deuteron. So the first thing is that the spin of deuteron is 1 and the parity is even. So we'll see how one can justify these numbers. Now, the total angular momentum I of the deuteron should be like, as we have discussed, that in deuteron there are only two nucleon, one is neutron, and the second one is proton, and these are the total angular momentum is the sum of the we can say the vector sum of these intrinsic angular momentum which arises due to the spin, as we have discussed in the previous lecture, and also due to the orbital motion. And we have discussed these orbital motion in nuclei arises due to the average potential of the nuclei. Now, where this S subscript N and S subscript P are individual spins of the nucleons, the neutron and proton, as the deuteron nuclei composed of only two nuclei. So these are the intrinsic angular momenta, and this is due to the motion due to the central potential of the nuclei. And the important thing is that this L is not regarding the one nucleon, but the orbital angular momentum of the nucleon as they move about their common center of mass is L. If you remember in my last lecture where we were discussing the potential, the interaction potential between the nucleons of this nuclei deuteron, there we have discussed the concept of reduced mass. So again this L arises once we are talking about the relative coordinates. So these are just to now we'll be looking how one can obtain this number 1 for a nuclei based on these descriptions which we have already discussed. So since the neutron and proton spins can be either parallel for a total of 1, that is half plus half 1, and or anti-parallel such that one is plus half, the other one is minus half, and then they just cancels out. So the net spin of the two nucleons can either give a total intrinsic momentum 1 or 0. So, and the orbital angular momentum is also there in that vector sum on the last slide, as I told you. So there are 4 ways to couple the spin of the neutron, the spin of the proton, and the angular momentum associated with the two nucleons, so that one can verify this total angular momentum equal to 1. And remember, we have also discussed that the parity of the deuteron is even. So based on those two things, we need to discuss these various possibilities now. So the first one is that the two spin are parallel and with L is equal to 0. If you remember last time, we have also discussed the deuteron regarding L is equal to 0. That is, in the same energy level, we can have these different possibilities that we will be discussing it, and then we will just conclude that which one is obvious in all these cases. The second one is the possibility when the two spin of the nucleons, the proton and the neutron, are anti-parallel such that the total intrinsic spin is 0 and L equal to 1. So if you remember on the last slide, the total angular momentum I is the sum of S and SP and this L. So if they are anti-parallel, so they will cancel out, and the total angular momentum will arise due to this L is equal to 1 due to the orbital quantum number. So since we are just discussing these possibilities, and then we will conclude which one is not possible and why it is not possible. So the third possibility is that the two intrinsic momenta, or we can say the spin, are parallel such that it gives you 1 and L equal to 1. And another possibility is that the two spin are parallel and with L equal to 2. These are the various representation, the parallel and anti-parallel concepts. Now, since, as I told you, that the parity of this nuclei is even, since we know that the parity of the deuteron is even, and the parity associated with the orbital angular momentum is determined by minus 1 to the power L, where L is the orbital angular quantum number. So since this will give us even, that is a plus quantity, based on this definition, if we make this L is equal to either 0 or L is equal to 2, so that this will give you even, since the Deuteron the parity is even. So the even parity arises if we are considering this first case or this last case. So the L is equal to 1 is not possible. So the observed even parity allows us to eliminate the combination of the spin that include L is equal to 1 and leaving the first one and the last one for L is equal to 0 and L is equal to 2 as possibilities. So the even parity can be obtained with this option 1 and also option A and option D, while L is equal to 1 do not contribute to that even parity, which is the observed even parity regarding the Deuteron. So we will just eliminate the two options, and then we will be concentrating with the first one and the last one. Now, once we have concluded the two aspects, the spin and parity and the total angular momentum, since in the last few lectures we have discussed these aspects regarding the nucleus, so now we are discussing the Deuteron, and generally we have discussed the magnetic dipole moment of any nucleus. So now the nucleus is Deuteron, which is the simplest nucleon-neutron interaction system. Now, if you remember on the last slide, I told you that we have two possibilities, L is equal to 0 and L is equal to 2. So if L is equal to 0 is perfectly correct description for the Deuteron, there should be no orbital contribution to the angular momentum. As I told you, the total angular momentum I is the sum of Sn plus Sp plus L. So if the total angular momentum I is 1, so that means this L should be 0. So we can assume that the total magnetic moment is simply the combination of the neutron and proton magnetic moment, that is, since the orbital angular momentum for L is equal to 0 do not contribute, that is regarding the S state, and then the total angular momentum of a nuclei will be due to the spin of the proton and neutron only, with no contribution from the orbital number. So in that situation, the magnetic moment definition, we have discussed these definition in our previous lecture, so there will be no magnetic moment associated with L since that L is equal to 0, so that do not contribute to any angular momentum. So the total angular momentum of a deuteron is due to the magnetic moment of the neutron and protons, and where these parameters are standard number that we have discussed previously and also given in various tabulated form. So if we talk the observed magnetic moment to be the z component of mu z when the spin have their maximum value plus half, such that the spin is 1/2 in the unit of h cut. So in that situation, this mu will be equal to this much in nuclear magneton. Now the observed value is around 0.8573 something in nuclear magneton. So if we just compare the observed number with the theoretical justification that we are discussing in this lecture, so it is in good but not quite exact agreement with the calculated values. So now we will see why there is a difference in the observed and the theoretical numbers if we just consider the L is equal to 0 possibilities. So for that we need to discuss the second possibilities on the previous slide. As I told you, the option A is one possibility, and the last one, the D option, where if you remember, with L is equal to 2. So since for L is equal to 0, the magnetic moment derived from these mathematics, which is just the equation for the magnetic moment of the neutron and proton only, with L is equal to 0. So there is not an exact agreement, almost perfect, but we will see how much it deviates. Now, in the context of the present discussion, we can ascribe the tiny discrepancy to the small mixture of the D state. Since, as I told you, L is equal to 0 is S state, we have discussed these things in my previous lectures, and L is equal to 1, which is not possible based on our discussion on the last few slides. That was P state. So the D state with L is equal to 0 is a possibility that it can give rise to that total angular momentum I equal to 1. So let's see what the situation is. So then in that situation, if you just represent the state wave function, that is the superposition of the L is equal to 0 and the L is equal to 2 state. So this is a way to describe and to see why there is a difference in the observed magnetic moment and the derived magnetic moment of the deuteron. So we have a deuteron calculating the magnetic moment from this wave function. Since we are just discussing these aspects, we will not be going into the detail, but rather doing so that is assuming the superposition of the two states. So in that regard, we have the two coefficient, and in that regard this is 0.96, which is due to the L is equal to 0, and this the coefficient AD square for the L is equal to 2 state, that is 0.04. So this means that the deuteron is 96% L is equal to 0, that is L orbit, S orbit, and only 4% with L is equal to 2, the D orbit. If you remember, L is equal to 0, L is equal to 2 was based on such numbers that it can give rise to the total observed angular momentum equal to 1. And since the magnetic moment based on the only for the wave function only for the S state do not give the observed value for the magnetic moment. So if we just use the superposition of the two, so that it gives a nice agreement, and then we can say that 96% of the deuteron corresponds to L is equal to 0, and then 4% with L is equal to 2. After the magnetic moment, we can now discuss the electric quadrupole moment of the deuteron. Since we have discussed the quadrupole moment of a nucleus in our previous lecture, and then there we have described the technical aspects, how quadrupole moment arises once the nuclei charge distribution deviates from the spherical symmetry. So when it gives rise to that characteristic field profile of the nuclei, and there we have discussed general aspects. So now we will be describing that thing for the nuclei deuteron. Now the proton and neutron have no electric quadrupole moment, so any measured non-zero value for the quadrupole moment must be due to the orbital motion. Intrinsically they do not have any quadrupole moment, so for pure L is equal to 0 wave function would have a vanishing quadrupole moment. So that means the observed quadrupole moment for the deuteron is this number. It's a small number, but this is measured in the unit bonds as we have discussed. So that hint us that with L is equal to 0 configuration for the deuteron will not give us the quadrupole moment. So it means it really is a mixture of L is equal to 0 and L is equal to 2 state. So the quadrupole moment, since L is equal to 0, will not give any quadrupole moment. So that means this whatever quadrupole moment is there, that is because of the L is equal to 2 state. So when the mixed wave function, as we have discussed, is used to calculate the quadrupole moment QD, the calculation gives two contribution terms. One is proportional to this AD square and the other is the ASAD. We have just not going into the detail, but rather we are just discussing it quantitatively, that why the quadrupole moment is there and why this L is equal to 0 is not the only possibility for the deuteron element to be in that particular substates. So where these are just the aspects how one can obtain that quadrupole moment based on these definition. Now to calculate this quadrupole moment, we must know the deuteron d state wave function, and it is not obtainable from the realistic phenomenological potential that we will be discussing in the coming few lectures. The d state admixture of the several percent of this calculation and is consistent with the 4% value deduced from the magnetic moment. So as I told you that this really to cost the wave function for the deuteron, we need to write it the superposition of L is equal to 0 and L is equal to 2 state. So how one can conclude this thing, that in case of the magnetic dipole moment, there is no reason to expect that it is correct to use the free nucleon magnetic moment in the nucleus. As I told you, there must be some contribution to the orbital angular momentum, and that is only comes when L is equal to 2 state. For the quadrupole moment, the poor knowledge of the d state wave function make the deduced d state admixture uncertain. Other experiments, particularly scattering experiment using deuteron as target, and also give d state admixtures in the range of 4%. Thus, our conclusions from the magnetic dipole and electric quadrupole moment may be valid after all. Now, it is important that we have an accurate knowledge of the d state wave function, because of the mixing of L values in the deuteron is the best evidence for the non-central tensile character of the nuclear force. As we have discussed this previously, what is meant by the non-central tensile component and all those things. Now, with this, I thank you for your time.